Imagine light itself growing tired. For most of your life, you've known the sun as something bright and immediate, a warmth on your skin, a reason to squint, a certainty overhead. But what if you could trace that light outward, past Mercury and Venus, past Earth's pale orbit, past Mars where it still feels like daylight, past the asteroid belt where it begins to thin, past Jupiter and Saturn where it becomes a distant lantern, past Neptune where blue twilight settles into a permanent dusk, and then keep going, keep traveling outward through the cold and dark, through regions where the sun's warmth becomes a whisper, its light a memory, until you arrive at a place so far from home that sunlight itself seems to have forgotten the way back. This is where we're journeying tonight, not to a place you can see or touch, but to a region of such profound distance and quietness that it reshapes how we understand the very structure of our solar system. Deep in that outer darkness, there exists an invisible shell of ancient ice and stone that orbits the sun in near total silence. No one has ever seen it directly. We cannot photograph it as we have photographed Saturn's rings or the craters of the moon, and yet it is perhaps one of the most haunting and beautiful facts of our cosmic neighborhood. Somewhere out beyond 2,000 times the distance from Earth to the sun, stretching to distances so vast that numbers themselves begin to lose meaning, there drifts an enormous cloud of primordial objects, remnants from the moment our solar system was born. This is the Oort cloud, and it has waited in the darkness for over 4 billion years, silent and patient, holding within itself the deepest mysteries of our solar system's ancient youth. What makes the Oort cloud so profoundly calming to contemplate is not merely its distance or its size, but what it represents: a frozen archive of time itself, a vast and peaceful graveyard of icy worlds that have remained largely undisturbed since the solar system's infancy. In all of human history, we have never sent a spacecraft to visit it. Our most ambitious explorers, the Voyager probes, will take tens of thousands of years to reach it, and even then, they will pass through only the outermost whispers of this vast sphere. That remoteness, that untouchability, speaks to something deeply calming about the universe, a sense that there are still places so far away, so undisturbed by human presence, that they remain purely themselves, purely a part of the cosmos as it was meant to be. If you've ever felt drawn to slow, deep dive stories about the hidden structures of space, the ones that ask you to imagine vast scales and ancient silences while settling into something quieter within yourself, you might find our channel devoted to these most relaxing facts about the Oort cloud and the deep solar system to be a steady companion. We create slow, narrated journeys into the cosmic distances and the scientific stories behind them, meant to ease your mind into wonder rather than leave you restless. If that calls to you, we'd be grateful if you'd subscribe and join us for more gentle explorations of the universe's most peaceful mysteries. Now, let us begin our descent outward, away from the sun's familiar warmth, toward that vast and tranquil cloud. Imagine first the transition from the familiar to the strange. Earth orbits at roughly 1 astronomical unit from the sun. That's the distance we use as our measuring stick, our reference point for the solar system. It takes 8 minutes for sunlight to reach us at this distance. Out at Jupiter, still well within what we think of as the inner solar system, sunlight takes 43 minutes to arrive. The planets grow dimmer, but they are still bathed in sunshine. You could stand on the surface of Neptune, the outermost classical planet, and the sun would appear as a brilliant blue-white star, small in the sky but still unmistakably bright, still quite capable of casting shadows and providing a sense of direction. But keep traveling, past Neptune's orbit, past the scattered disk of icy bodies that marks the outskirts of the planets, past Pluto and its siblings in the Kuiper belt, where sunlight has taken more than 5 hours to arrive and appears perhaps no brighter than the full moon does from Earth. Continue on, now leaving behind everything we have ever photographed or studied in close detail, moving into regions that exist for us only as inference, as mathematical prediction, as quiet deduction based on the patterns of distant comets. The journey to the Oort cloud is not a journey across years or centuries or even millions of years. It is a journey through a void so profound that it takes on the quality of a meditation. 2,000 astronomical units from the Sun, the inner boundary where the Oort cloud begins, is a distance of nearly 300 billion kilometers. The light from the Sun takes 1 month to arrive at that distance. Stand there in imagination and look back. The Sun is still a point of light, a pale star among billions of others, noticeably brighter than the background stars perhaps, but diminished, humbled by distance. But the Oort cloud does not stop there. Some estimates suggest it extends as far as 200,000 astronomical units, a region so vast that we cannot yet measure it with any precision. Light from the Sun at that distance takes 2.5 years to complete the journey. From this vantage point, from the very edge of our solar system, the Sun is nearly indistinguishable from other nearby stars. It is simply one faint point of light in an ocean of faint points of light. You are standing, in imagination, at the threshold between the solar system and true interstellar space, in a place so distant and so cold that it feels as though it exists in a different universe entirely, and yet it remains gravitationally bound to that faraway Sun, still orbiting, still part of the family of the solar system, even as it drifts on the very border between home and the endless cosmos beyond. What makes this calm, this particular way of understanding these vast distances, is something we rarely speak of directly. It is the realization that between you and the Oort cloud, there is almost nothing. Space is almost entirely empty. The light that takes 1 month to reach the inner edge of the Oort cloud crosses distances so vast that if you were to compress them in any meaningful way, there would still be nothing to compress. The void between the outermost planets and the beginning of the Oort cloud is a nothingness so complete that it creates a kind of peace. In that emptiness, sound cannot travel, heat cannot propagate. There are no collisions, no violence, no rushed activity. There is only the slow, patient drift of small icy bodies through an ocean of cold and dark, turning their ancient orbits while the universe ages around them. And so, as you drift further into the particulars of this place, it becomes necessary to sit with a question that astronomers have long wrestled with in the quiet hours of their own contemplation. How do you hold something so immense in your mind that exists almost nowhere at all? The Oort cloud begins somewhere beyond the orbit of Neptune, that distant blue-grey world you might recognize from childhood planetarium visits, and it extends outward in a gradual, almost imperceptible thinning that takes you 2,000 times farther from the Sun than Earth is. 2,000. Then the cloud continues stretching, spreading, until at its outer boundary, which is itself only theoretical, only a mathematician's educated whisper, it reaches perhaps 200,000 times that same Earth-Sun distance. To offer a gentler frame for this vastness, if the distance from Earth to the Sun were reduced to the thickness of a single sheet of paper, the Oort cloud would be a sphere larger than a small city, hollow and mostly empty, holding within it only the tiniest specks of ice and stone. Consider for a moment the nature of this emptiness. In the solar system closer to home, you have the planets, the asteroid belt with its millions of tumbling rocks, the Kuiper belt beyond Neptune with its icy bodies crowded in comparative intimacy. But here, in the Oort realm, those objects, and there may be trillions of them, are so scattered, so profoundly isolated from one another, that if you were somehow to stand upon one tiny comet nucleus, you might never see another throughout an entire human lifetime. The darkness would be complete, the silence absolute, and your neighbors would orbit in their own separate paths millions or billions of kilometers away, moving in a slow waltz that takes hundreds of thousands of years to complete. This is a stillness unlike any you might experience on Earth. It is not the stillness of a sleeping forest, because even there the breeze moves, microorganisms pulse with life, the planet beneath rotates. No, this is something more profound, a preservation, almost, of ancient material that has drifted unchanged since the solar system was still young, still settling into the shape we know today. And as you imagine these frozen remnants turning in their slow orbits, waiting in an outer darkness where the sun itself becomes nothing more than the brightest star in a field of countless other stars, you might feel a strange sense of peace descend. The Oort cloud is, in many ways, a monument to deep time and cosmic patience. It asks us to expand the boundaries of what we consider home, to recognize that the familiar solar system of 8 planets and their moons represents only the brightest, busiest chapter of a far vaster story. The true solar system, the one we are now learning to contemplate, extends into realms where sunlight becomes a whisper, where gravity itself seems to fade into insignificance, yet still tethers billions upon billions of ancient wanderers to their slow and eternal paths. And if you find yourself drawn to these journeys through the quieter provinces of space, these slow, patient explorations of what lies beyond the common knowledge, beyond the rushing modern world, I invite you to subscribe to this channel. Here we linger in the cosmic dark, we move at the pace of sleeping thought, and we uncover the gentle truths that dwell in the spaces between the stars. There are many more such voyages yet to take, many more thresholds of wonder to cross, and each one awaits you in the same unhurried, thoughtful company. The Oort cloud itself remained invisible to human eyes for most of history, known only through inference and calculation. Its very existence is a kind of ghost story, a tale that emerged not from direct observation, but from a peculiar pattern of misbehavior, from comets that appeared where they should not have been, moving in orbits that spoke of an origin far deeper in cosmic time than anyone had initially suspected. The story of how astronomers came to suspect this vast invisible shell began not with telescopes peering outward, but with puzzles falling inward. Throughout the early 20th century, astronomers noticed something peculiar about certain comets. Their orbits didn't quite behave as expected. These were the long-period comets, the wanderers that took hundreds or thousands of years to complete a single journey around the sun, and their paths seemed to originate from a region no one could quite see or fully explain. It was in 1932 that an Estonian astronomer named Ernst Öpik, sitting quietly with his calculations, began to wonder aloud about where these strange visitors might be coming from. Öpik proposed, with careful thoughtfulness, that there must exist far beyond the known planets, a vast shell or halo of icy bodies, a sort of cosmic reservoir surrounding the solar system. His musings were elegant and grounded in mathematics, yet they remained somewhat in the background of astronomical conversation for decades, like a half-remembered dream that lingers even when you cannot quite grasp its meaning. It was not until after the Second World War that this old question would find its clearest voice. In 1950, a Dutch astronomer named Jan Oort undertook a meticulous study of comets whose orbits were particularly long and whose trajectories seemed almost random in their approach to the inner solar system. Oort, working with remarkable patience and precision, analyzed the orbital data of many comets and began to notice statistical patterns emerging from what appeared to be chaos. When he plotted the orbits on paper, a shape began to resolve from the noise. Not a disk, not a tightly bound system, but a vast spherical shell extending far, far beyond Pluto. Oort's calculations suggested that this shell must contain an enormous number of icy bodies, and that the long-period comets we observe today are stragglers knocked loose from this distant reservoir by gravitational perturbations. His work, gave mathematical substance to what Oort had intuited, transforming speculation into scientific hypothesis. The region came to bear Oort's name not out of any effort to claim it, but because his calculations were so thorough and convincing that they provided the framework upon which all subsequent thinking would be built. What is remarkable, when you sit with this history, is how much of it was invisible work. Oort never saw the cloud itself. No one has ever seen it, nor will anyone living today. His conclusions rested entirely on the behavior of objects that occasionally tumbled inward from its depths, leaving traces in the form of comets. He reasoned backward, in a sense, from the visible to the invisible. He examined the comets that arrived, studied their velocities and angles, and asked himself, where could they have come from? What reservoir would need to exist to explain their numbers, their randomness, their distribution? The answer crystallized slowly, as all good answers do, through careful observation and the patient arithmetic of celestial mechanics. In that moment, the late 1940s, moving into 1950, the conception of the solar system underwent a profound transformation. It had been understood as a relatively neat affair. The Sun, the 8 or 9 planets, a scattering of asteroids between Mars and Jupiter, and beyond that, space. But Oort's work revealed something far more expansive and mysterious. The true boundary of the Sun's gravitational realm extended not just to Neptune or Pluto, but far beyond, to distances so vast that light from the Sun, though still nominally its light, arrived as little more than a whisper. The solar system, it seemed, was far larger and stranger than anyone had truly appreciated, and at its outer limit drifted billions upon billions of remnants from its birth, silent witnesses to creation itself. The real puzzle that drove Oort and his colleagues toward their revolutionary thinking began not with distant observation, but with something far more immediate and unsettling. Across the centuries and decades of careful astronomical record-keeping, astronomers had noticed something peculiar about the comets that appeared without warning in Earth's skies. These were not the familiar periodic visitors, the ones whose paths could be predicted and plotted with growing confidence as their orbital periods became known. No, these were something altogether stranger. These were the long-period comets, the ones that arrived on trajectories so unusual, so improbably angled and inclined, that they seemed almost to come from random directions across the celestial sphere. Halley's Comet and a handful of others had become predictable friends, returning on schedule like clockwork. But most comets came from nowhere, or so it seemed. Now, here is where the logic began to tighten. When astronomers calculated backward the original orbits of these strange visitors, before the Sun's gravity had bent and drawn them inward, they found something remarkable. These comets were not arriving from the direction of the planets, not following the neat ecliptic plane where Earth and Jupiter and Saturn peacefully orbited. Rather, they seemed to be coming from all directions at once. From above the plane of the solar system, from below it, from the sides, from every conceivable angle, as though the sky itself was studded with these icy bodies, waiting only to be nudged toward the inner system. It was a distribution that made no sense if comets originated in the orderly region of Neptune and Pluto, those distant planets whose orbits lay flat and predictable. What would cause such a spherical, omnidirectional cloud of icy bodies to exist in the first place? The answer, when it emerged from Oort's calculations, was almost impossibly elegant. If there existed a vast reservoir of comets, not scattered at random, but gathered in a great spherical shell surrounding the entire solar system, far beyond even the distant orbit of Pluto, then the directional chaos became understandable. Any small perturbation, any gentle nudge from a passing star, or the slow tugging of the galaxy itself, could knock one of these bodies from its ancient path. And once knocked loose, it would tumble inward on an orbit that could take it from any direction, creating exactly the pattern astronomers were observing. The beauty of this inference was that it required no exotic new physics. It required only that we accept what the observations were already telling us. The long-period comets were not freakish anomalies, they were messengers, arriving from a distant reservoir that had existed since the solar system's infancy. Their strange orbits were not evidence of chaos or randomness, but rather evidence of an orderly, vast structure at the periphery of everything we knew. Consider for a moment what this meant conceptually. The solar system, as understood in the early 20th century, was supposed to end somewhere beyond Neptune and Pluto. Those were the known planets, the final curtain call. But the comet data was insisting on something larger, something older. There was more to the story. There had to be a shell, a halo, an invisible architecture of icy bodies surrounding everything like an eternal guardian. And if that shell existed, if billions upon billions of icy remnants were drifting out there in the deep cold, then the solar system itself was not a compact, neat little island in space. It was something far more vast and lonely and profound. The mathematicians and astronomers who worked through these calculations must have felt a peculiar mixture of excitement and unsettledness. The universe had just become simultaneously more elegant in its logic and more immense in its scale. The data were not contradicting each other. They were revealing a hidden layer of reality that had been there all along, patiently waiting for someone to know how to listen to what the comets were saying. Now, to truly understand what astronomers mean when they speak of the Oort cloud, we must sit with the numbers for a moment, not to overwhelm, but to let the vast stillness of them settle into your mind, like snow falling through darkness. The inner edge of this cosmic shell begins somewhere around 2,000 astronomical units from the Sun. 2,000 times the distance between Earth and our star, a figure that already seems to stretch beyond comprehension. And yet, the Oort cloud does not end there. It continues outward, shell upon shell of frozen silence, reaching perhaps 200,000 astronomical units into the void. 200,000. Some estimates suggest it may extend even further, though the cloud's outer boundary remains, by necessity, a matter of gentle speculation. Let yourself pause on what this actually means. If you were to travel at the speed of light, the fastest anything can move in our universe, the journey from the inner edge of the Oort cloud to the outer would take you months to cross. From Earth to the inner Oort cloud would consume over a year of constant light-speed travel. And remember, we have never come close to building a spacecraft capable of such speeds. The fastest human-made object ever, the Parker Solar Probe, moves at perhaps 200 kilometers per second. At that velocity, the journey to the inner Oort cloud would require roughly 3 million years. The emptiness contained within these distances is almost unimaginable. Within the space occupied by the Oort cloud, there is not a crowded forest of comets, but rather an almost perfect void. Imagine, if you will, spreading 100 billion objects, perhaps as many icy bodies as there are stars in our galaxy, across a region of space so immense that the average distance between any two of these objects would be measured in millions of kilometers. Loneliness upon loneliness. Isolation carved into the architecture of space itself. At 2,000 astronomical units, the sunlight that burns so brightly in Earth's sky has dimmed to something almost indistinguishable from the background starlight. The sun itself, that blazing sphere that seems so impossibly distant when viewed from Neptune, becomes merely another star, faint, unremarkable, and cold. By the time you approach 200,000 astronomical units, the sun is simply one point of light among countless others, providing almost no warmth, almost no perceptible gravity, almost nothing that might anchor these frozen wanderers to their parent star. This is what the emptiness truly means. It is not the emptiness of a room, or even the emptiness of space between planets. It is the emptiness of eons compressed into geometry. These vast distances mean that the Oort cloud exists in a state of profound isolation. Each comet, each icy nucleus, separated from its neighbors by gulfs so wide that the concept of proximity loses all meaning. For an object drifting in the outer Oort cloud, there is no nearby companion, no cosmic neighbor to break the visual monotony. There is only the eternal dark and the slow rotation of distant stars overhead. And yet this emptiness is not empty of purpose or history. Within these distances lies preserved something precious, a record. Each object in the Oort cloud is a messenger from the chaotic dawn of the solar system, a fragment untouched by planetary processes, unchanged for 4.5 billion years. The vast distances that make the Oort cloud seem so barren and hostile are precisely what make it a sanctuary, a deep freeze archive where the oldest memories of our cosmic origins remain locked away. The numbers, 2,000 to 200,000 astronomical units, are not merely figures to be memorized. They are an invitation to imagine the vastness that surrounds us, the protective shell of frozen silence that orbits far beyond the reach of human experience or even human intention. In these distances, in this emptiness, there is a strange kind of peace. Imagine the solar system as it was, not in the gentle, orderly arrangement we know today, but as a churning, violent nursery of creation. 4.5 billion years ago, in those first few 100,000 years after the sun ignited, something quite extraordinary and thoroughly chaotic was unfolding in the space where planets would eventually settle. The leading theory of how the Oort cloud came to exist begins not in the distant reaches where we find it now, but much, much closer to the Sun, in the region where Jupiter and Saturn were themselves still learning their place in this young solar system. Picture, if you will, countless planetesimals, these small, icy and rocky bodies, most of them only a few kilometers across, some larger, drifting through the primordial disk of dust and gas that surrounded our nascent star. These weren't organized or quiet. They were colliding, merging, occasionally shattering. They were the building blocks from which planets would form, and they numbered in the trillions, perhaps quadrillions, scattered throughout the inner and middle regions of the solar system's early architecture. The story of the Oort cloud, as we understand it through decades of computational models and astronomical detective work, is fundamentally a story of cosmic violence followed by exile. As the gas giants, particularly Jupiter and Saturn, grew larger and larger, accumulating mass and gravitational power, they began to exert tremendous influence on everything around them. These massive worlds, moving in their increasingly confident orbits, encountered countless planetesimals, and each encounter was a moment of gravitational reckoning. Some of these small bodies were pulled into collision courses with the planets themselves. Others were accelerated, flung like cosmic projectiles into new trajectories. And it is this scattering, this gravitational billiards game played out over millions of years, that explains how material originally formed in the warm inner solar system ended up in the frozen dark, far beyond the orbits we've come to know. The mechanism is almost meditative in its inevitability. A planetesimal, drifting along in its modest orbit, perhaps in the region where the asteroid belt might form, encounters the immense gravity well of Jupiter. The interaction doesn't destroy the planetesimal, but it fundamentally alters its destiny. Its velocity increases, its orbit becomes elongated, stretched, and in that moment of encounter, the object is flung outward, sent on a journey toward colder and more distant regions. This happened countless times, again and again, a vast echoing dance of gravity and motion. Each ejection moved a planetesimal further from the Sun, and as more and more objects were scattered in this way, they were pushed progressively outward, accumulating in regions farther and farther from the solar furnace. What draws the mind to rest in contemplating this process is its sheer scale and randomness. These weren't precise, directed mechanisms. They were stochastic events, probabilistic, contingent, shaped by the particular initial conditions that existed in the solar system 4.5 billion years ago. A planetesimal that encountered Jupiter at one angle might be sent to a distance of 5,000 astronomical units. Another, meeting the same planet only slightly differently, might be propelled to 20,000. The cumulative effect, however, produced something coherent, a vast reservoir of scattered, exiled bodies distributed in an increasingly spherical shell around the nascent solar system. Saturn too played its role in this cosmic displacement. The second gas giant, less massive than Jupiter but still towering in gravitational influence, also scattered planetesimals. In fact, according to contemporary models, Saturn may have been particularly efficient at launching objects into the far reaches. As these two great worlds migrated through the early solar system, and they did migrate, slowly shifting their positions as they interacted with the disk of remaining material, they created waves of disruption. Planetesimals that had formed in relatively stable orbits found their positions suddenly untenable. They were caught in gravitational currents, swept outward and away. Consider for a moment what would have been the fate of any observer watching this process unfold. The early solar system would have appeared far more crowded, more dynamic than the relatively serene place we find today. Comets would have been frequent, streaking through the inner solar system on catastrophic trajectories. The bombardment of the inner planets would have been intense, a cascading rain of impacts that shaped and reshaped the surfaces of Mercury, Venus, Earth, and Mars. It was violent and unstable, and yet it was also the crucible in which Earth itself acquired much of the water and organic compounds that would eventually nurture life. The planetesimals that were scattered outward, however, were largely spared from the collisional chaos that continued in the inner system. They were not exiled to oblivion, but, rather, to dormancy. They were placed into orbits that took them so far from the Sun that they would remain largely undisturbed for billions of years. The gravitational kicks that sent them away also placed them in regions where they were unlikely to collide with one another. Space, even in the Oort cloud, is so vast that the density of objects, though we speak of it as a cloud, is extraordinarily low. Two objects in the Oort cloud might be separated by millions of kilometers, drifting in their individual orbits, never knowing of one another's existence. The beauty of this origin story, and perhaps beauty is not too strong a word, lies in how it connects the Oort cloud to the very birth of our planetary system. These objects we speak of, these icy bodies that now populate the outer reaches of the solar system, they are not merely debris or cosmic pollution. They are, in a profound sense, the preserved remains of the solar system's formation. They carry within them information about the conditions that existed in the primordial disk, the temperatures and compositions and chemical signatures of an era that is otherwise wholly inaccessible to us. They are messengers from the deep past, silent custodians of the solar system's infancy, drifting now in their appointed places, waiting in the dark for the gravitational perturbations that might, after billions of years, send them back toward the sun and the light. The early solar system was not the serene, orderly place we inhabit today. In those first few million years, as gravity pulled dust and gas into increasingly massive bodies, something far more dramatic was unfolding in the region where Jupiter and Saturn were rising toward their eventual dominance. Picture, if you will, the young gas giants still settling into their orbits, their gravity wells immense and barely constrained, reaching outward like invisible hands into the surrounding debris field. These newborn titans were not passive observers of the solar system's formation. They were sculptors, and the material around them was clay awaiting their touch. The planetesimals that would eventually populate the Oort cloud were already in motion during this period. Small bodies, some a few kilometers across, others larger, all orbiting in the intermediate zones between what would become the inner planets and the great outer void. Jupiter's gravity, perhaps the most powerful force in the solar system at that time, began to interact with these icy bodies in ways both dramatic and subtle. When a small planetesimal ventured too close to Jupiter's path, one of two fates typically awaited it. It might be captured into orbit around the giant planet itself, or, more often, it would experience what astronomers call a close gravitational encounter, a moment of profound deflection that would completely alter its trajectory through space. These encounters were rarely gentle. Imagine a small icy body drifting through the protoplanetary disk when suddenly the immense gravity of a young Jupiter intercepts its path. The planetesimal's velocity would shift dramatically, its orbit transforming in an instant from a relatively mild ellipse into something far more eccentric and elongated. Saturn, though somewhat less massive than Jupiter, was experiencing its own formation and exerting its own powerful gravitational influence on the surrounding material. The combined effect of both giants working in tandem, their orbits and gravitational fields interacting over millions of years, created what astronomers now describe as a scattering or dispersal event of remarkable scale. What makes this process so fascinating and so essential to understanding the Oort cloud is that it operated not through violent collisions, but through what we might call gravitational resonance, a kind of cosmic choreography in which the proper timing of gravitational encounters could accumulate their effects. A planetesimal might receive a small kick from Jupiter, then drift outward slightly. Millions of years later, a distant encounter with Saturn, or perhaps Jupiter again, could impart another deflection. Each individual encounter might seem minor, but collectively, over the course of several million years, these interactions had the power to reshape entire populations of bodies. The particularly elegant aspect of this process is that it specifically tended to scatter material outward, away from the inner solar system and beyond the current orbital territories of the giant planets. When a planetesimal is on a collision course with a massive object, gravity doesn't simply swallow it. Instead, it often whips the smaller body backward, like a tennis ball bouncing off a returning racket. This scattering mechanism was especially effective because the giant planets were still positioned relatively close to their formation sites. They hadn't yet migrated into their modern orbits. The young Jupiter and Saturn, through billions of gravitational encounters with the primitive planetesimals, were essentially clearing their neighborhoods, flinging billions of icy bodies outward into what would become the Oort cloud. Why would these bodies scatter outward rather than inward toward the Sun? The answer lies in orbital mechanics and the particular geometry of these encounters. When a small body approaches a massive object from the orbital direction, from behind or alongside, the gravitational encounter typically redirects it outward, away from the central star. It is a process not unlike a gravitational assist maneuver that modern spacecraft utilize to gain speed and momentum, except here, the effect is to increase the orbital energy of planetesimals, sending them on longer, more elongated paths that carried them ever farther from the Sun's warmth. This scattering occurred not as a single event, but as a continuous process spread across millions of years. The first icy bodies began their ejection into the outer darkness, perhaps 4.5 billion years ago, when the solar system was still young enough for the giant planets to be in active gravitational conversation with the surrounding debris. Some planetesimals received multiple encounters, being bumped and redirected several times as they made their way outward. Others needed only a single powerful gravitational assist to achieve the orbital energy necessary to be cast into the deep. Over this extended period, the process gradually sorted the solar system into its layers, inner rocky planets stabilizing in their modern orbits, giant planets establishing their kingdoms in the outer solar system, and billions upon billions of icy remnants being progressively and inexorably scattered beyond. The beauty of this mechanism, from a narrative perspective, is that it explains not only how the Oort cloud came to be populated, but also why its objects possess the particular orbital characteristics they display today. Those strange, elongated paths that long-period comets follow when they venture inward from the cloud. Those eccentric orbits are themselves a fossil record of this ancient scattering event. Each unusual trajectory is a kind of memory, a gravitational echo of an encounter that occurred in the solar system's first few million years, before the giant planets had fully established their modern configuration. And so, through this gentle but relentless process of gravitational encounter and orbital deflection, the young Jupiter and Saturn became the architects of the Oort cloud. They did not create the material that had condensed long before from the solar nebula, but they shaped its distribution, redirected its motion, and flung it outward into the darkness. In doing so, they established one of the solar system's most remarkable features, a vast, invisible reservoir of ancient, icy bodies, scattered and preserved at incomprehensible distances, waiting in the cold stillness for the occasional nudge that would send one of them on a journey back toward the sun. Now, within this vast and shadowed realm that extends so impossibly far from the sun, there exists a subtle geography that astronomers have come to understand, a distinction between two nested zones, each with its own character and origin story. The inner boundary, the region nearest to our planetary neighborhood, holds what some researchers call the Hills cloud, named for the astronomer Jack Hills who studied its properties in the 1980s. This inner shell, if you can imagine it, forms a kind of denser halo that begins somewhere beyond Neptune's orbit, perhaps at distances of 2,000 to a few tens of thousands of astronomical units from the Sun. It is here, in this first frontier of deep space, where the gravitational influence of the solar system remains relatively more pronounced, more tangible in the way that gravity can ever be tangible across such incomprehensible voids. The Hills cloud, you might say, represents the inner sanctum of this frozen archive, closer, more accessible in the way that nothing out here is truly accessible, yet still so impossibly remote that light from our sun, though it travels at the speed of light itself, requires hours and hours to arrive as a faint whisper of illumination. And then, beyond this inner shell, stretches the true and vast Oort cloud proper, the outer sphere that extends to perhaps 200,000 astronomical units, or even beyond. Picture, if you can, a gradual thinning as distance increases, a transition from one realm to another, not marked by any physical boundary, but by the gentle fading of density, the slow dispersion of icy bodies across ever greater volumes of emptiness. The outer Oort cloud, this diffuse spherical halo that surrounds everything we know, represents the true frontier of the Sun's gravitational domain, the place where the tug of our star becomes so faint, so gossamer thin, that a passing star from the galactic neighborhood might begin to exert influence as powerful or even more powerful than the Sun itself. Is there a hard line where one ends and the other begins? The answer is no, not truly. The distinction between the Hills cloud and the outer Oort cloud is one born more from the mathematics of orbital dynamics and the behavior of bodies within these zones than from any sharply defined boundary carved through space. What makes this distinction meaningful, though, is what it tells us about the physics at work. The inner Hills cloud, existing in closer communion with the Sun's gravity, tends to shelter objects in more stable, more predictable orbits. These are the remnants that were scattered outward early in the solar system's history, tossed beyond the planets by Jupiter and Saturn's gravitational maneuvers, yet not cast so far that they wholly escaped into interstellar oblivion. They remain, in a sense, loosely bound to the solar system, held by gravity that, while phenomenally weak at such distances, is nonetheless constant and eternal. And perhaps you notice something calming in this idea, that even here, in the deepest dark beyond the furthest worlds we know, there is still a kind of order, a structure born from the deterministic dance of gravity. The outer reaches, by contrast, where the cloud becomes so diffuse that individual objects might drift for millions of years without encountering even a single companion, represent a realm where the sun's authority grows phantasmal. These are the places where a passing star, one of the countless suns that drift through the Milky Way, can reach out with its own gravitational fingers and pluck an object loose, nudging it onto a trajectory toward the inner solar system. This is where the boundary between ours and theirs, between solar and interstellar, grows not merely thin but conceptually fluid. The outer Oort cloud, then, serves as a kind of demilitarized zone, a region where the sun's dominion is real but waning, where the galaxy's vast influence looms ever larger and more significant. Astronomers, in their careful way, have recognized that this two-zone model helps explain certain observations about the comets we do see. The objects that venture inward from the inner Hills cloud might behave differently, might reveal different orbital characteristics than those arriving from the deeper depths. And while these ideas remain under scrutiny and revision, as our observations grow more refined, they paint a picture of surprising internal complexity within what might seem, from afar, merely a uniform shell of icy exile. There is, in this subtlety, something worth holding in your mind as you contemplate the vast architecture of our cosmic neighborhood. The recognition that even in emptiness, even in the coldest, darkest places imaginable, there exist gradations, neighborhoods within neighborhoods, a kind of spatial grammar written in the language of gravity and distance. And so we arrive at the objects themselves, the small, silent inhabitants of this vast frontier. These are not the dramatic ice giants or the massive rocky planets that shape the inner solar system's architecture. Instead, the Oort cloud is populated by countless bodies of humbler scale, each one a relic of the solar system's birth, each one a wanderer in an almost unimaginable expanse of darkness. The objects themselves, we believe, range typically from just a few kilometers in diameter up to perhaps 20 or 30 kilometers, though some speculation suggests occasional larger bodies might lurk in the deeper reaches. Picture, if you will, a boulder the size of a small mountain, or a rocky island drifting alone through the void, with no ground beneath it, no ocean around it, only the whisper-thin vacuum of space pressing inward from all directions. These bodies are composed of what astronomers call ices, and this word carries a particular meaning in the cosmic lexicon. It is not simply frozen water, though water ice certainly forms a significant portion of their makeup. Rather, these distant objects are blended from frozen volatiles, the chemical compounds that only remain solid in the deepest cold. There is methane ice, ammonia ice, carbon monoxide frozen into crystalline form, and water ice binding it all together in an intricate mineral architecture. Scattered throughout this icy matrix are silicate rocks, the same fundamental building blocks of terrestrial worlds, mixed and bound with the frozen gases into a kind of cosmic composite. What are these objects, really, but time capsules from an age when our solar system was still young and hot and chaotic, fragments that escaped capture by the giant planets and were cast outward to this quiet exile? The darkness out here is almost absolute. We cannot see these bodies with our telescopes from Earth, not because they are too small, though they are, but because they are so extraordinarily distant and because they reflect almost no sunlight. The sun, at such vast distances, appears not as a disk, but as merely the brightest point in a field of stars, a luminous beacon reduced to insignificance. Any light that does strike an Oort cloud object is reflected with the faintest efficiency. These bodies have been exposed to cosmic radiation, to the slow battering of charged particles from the galactic environment, for billions of years. The surfaces of many have darkened, acquiring a thin crust of complex organic molecules. We might call them tarry, or blackened, a coating that makes them even less reflective than one might expect. The temperatures here, they are almost incomprehensible in their severity. We are speaking of regions where the ambient temperature hovers near absolute zero, perhaps a few dozen degrees above it. At such cold, all motion ceases at the atomic level. Chemical reactions that would proceed at measurable rates in warmer environments simply freeze into stillness. Time itself seems to slow, or perhaps it is our perception of time that slows when contemplating such profound quiet. The warmth from the distant sun provides almost no energy whatsoever. Any residual heat within these objects, any warmth that might have been trapped from the solar system's formation epoch billions of years ago, has long since radiated away into the void. These are corpses of a sort, frozen remnants awaiting a gravitational nudge that might, or might not, come in the next million years. And yet there is a strange peace in imagining them. Each body drifts in isolation, moving through the void at speeds that sound rapid, but which, when placed against the cosmic distances involved, reveal themselves as infinitesimal. An Oort cloud object might travel at a few kilometers per second relative to the sun, a velocity that would take hours to traverse even a small distance by our human perception of travel. But set against the billions of kilometers between objects, this becomes almost a suspension, a near motionlessness. The separation between neighboring bodies is so vast that any two adjacent chunks in the Oort cloud are likely separated by millions of kilometers of empty space. Some estimates suggest that encounters between objects are so rare that even over the entire history of the solar system, collisions would be vanishingly uncommon. It is hard to imagine loneliness of this order, this profound isolation. These objects represent, in a sense, the solar system's most ancient archaeology. They contain, preserved in their ices and minerals, chemical signatures from the very earliest moments of stellar formation. The organic compounds embedded in their surfaces carry information about the chemical environment of the nebula from which all planets and moons and asteroids condensed. When a comet from the Oort cloud is nudged inward toward the sun and eventually toward our telescopes and space probes, it brings with it this ancient message, this small, frozen letter from the deep past. In their stillness and cold and darkness, these bodies have been waiting, patient and unchanging, for anyone who might wish to listen to their story. Picture yourself at the edge of where human experience fades into pure imagination. The Oort cloud exists in a realm so distant, so utterly removed from the warmth and light we know, that it might as well belong to another universe entirely. And yet it is ours, spinning silently at the threshold of our solar system's dominion. The sun, that great furnace around which all our days are organized, becomes something almost unrecognizable out here. From Earth, we feel its heat on our skin. We see its brightness flooding the sky at noon. But imagine traveling outward, farther and farther, watching that familiar yellow disk shrink and dim with each vast stride. By the time you reach the Oort cloud, the sun is no longer a source of warmth or life. It is barely a star at all. It becomes instead a point of light, perhaps as bright as the full moon appears to us on a clear night, or dimmer still. To the objects drifting in the deepest reaches of this cloud, our sun looks like just another star scattered across the void, indistinguishable from Venus or Sirius, or any other pinprick of luminescence scattered through the black. The concept of day and night loses all meaning. There is only darkness, and at the very center of that darkness, a whisper of light so faint that it offers no warmth whatsoever. And the cold. The cold is perhaps the most essential truth of the Oort cloud. We speak of temperature in various ways down here on Earth. We know winter as cold, and we shiver. We know the depths of Antarctica, where the mercury barely climbs above 40 degrees below zero. We know the coldest places our scientists have managed to create in laboratories, chilled to near absolute zero through elaborate machinery and focused human effort. But the Oort cloud achieves temperatures that rival those artificial extremes simply by existing at such distance from the only heat source that matters. The objects that drift there exist in a state of profound, ancient cold. We estimate the temperature there hovers somewhere between 35 and 50 Kelvin, which translates to roughly -230 to 220 degrees Celsius. Some regions, those pushed even farther into shadow, might be colder still, drifting toward absolute zero, that theoretical temperature at which all molecular motion ceases, which sits at -273.15 degrees Celsius, a point of absolute stillness that the universe approaches but never quite reaches. At such temperatures, substances behave in ways utterly foreign to our experience. Water ice, which falls gently as snow on a winter afternoon, becomes hard as granite, harder perhaps, brittle and unchanging. Volatiles that we might think of as gases, methane, ammonia, carbon monoxide, carbon dioxide, freeze solid, locked into crystals that have remained undisturbed, unmelted, unwarm for billions of years. The icy bodies that compose the Oort cloud are not the icy bodies we might imagine from comets we've observed passing closer to the sun. They are something more fundamental, frozen archives, locked in a state that preserves them almost perfectly against the slow degradation that time brings everywhere else. What does such cold do to the passage of time itself? Not literally, though Einstein's equations would suggest that even subtle differences in gravitational fields create minute variations in how time flows. But psychologically, spiritually even, the image of such profound cold speaks to a kind of stillness that is almost meditative. These icy remnants drift in near absolute silence, in near absolute darkness, in cold so complete that they have changed barely at all in the 4.5 billion years since they first formed. They are, in a sense, frozen in time. The darkness and the cold work together, creating a realm that is almost beyond comprehension. In such conditions, there is no erosion as we know it, no weathering, no subtle wearing away of surfaces by radiation or heat, or the gentle touch of warmer air. There is only patience. There is only the slow, eternal drift through the vacuum, the faint pull of gravity from the distant sun, and the vast emptiness surrounding everything. The Oort cloud objects exist in what we might call the slow cold, the stillness of deep time, the peace of a place where nothing happens, where change comes only in the smallest increments, over the grandest scales imaginable. And perhaps that is why the Oort cloud feels so restful to contemplate, even though it exists in conditions no human could survive for even a moment. It represents a kind of ultimate rest, a final stillness, a place where the universe has settled into an almost perfect stasis. The cold preserves everything, the darkness conceals everything, and together they create a realm that feels, paradoxically, like profound tranquility. In the profound stillness of the Oort cloud, where objects drift in what seems like eternal repose, a subtle truth emerges. Nothing remains truly undisturbed. Even in this sanctuary of ice and silence, far from the sun's warming glow, forces work patiently across the vast stretches of time, nudging these ancient remnants from their slow, solitary journeys. The Oort cloud does not exist in isolation. It floats, instead, within a galaxy, the Milky Way, and galaxies are anything but static realms. Picture, if you will, the sun and its distant retinue of icy bodies moving through space as part of a larger stellar neighborhood. Every few million years, a passing star drifts relatively close to our solar system, traveling through the darkness on its own long orbit around the galactic center. When that happens, something remarkable unfolds in the Oort cloud, though the change is so gradual that it would be imperceptible to any observer. The gravity of that passing star, though distant, exerts a subtle pull on the outermost objects in the cloud. It is a tug so gentle that it might take millennia to noticeably alter an object's trajectory, yet over time, these gravitational whispers accumulate. What precisely occurs during such an encounter? An Oort cloud object orbiting the distant sun finds itself caught, momentarily, in a competition of gravitational forces. The star passing through the neighborhood tugs with its own gravity, while the sun pulls back. The result is a perturbation, a slight, almost imperceptible shift in the object's path. Some objects experience accelerations that push them farther from the sun, outward into the interstellar deep. Others, however, experience something different. They are nudged inward. This inward nudging is the mechanism that transforms a dormant, frozen wanderer of the deep outer solar system into something far more dramatic, a returning comet. An object that has drifted invisibly for millions of years suddenly begins a long, slow descent toward the inner planets. This journey may take tens of thousands of years. As it approaches the sun, the heating increases, ever so gradually. Volatiles, ices of methane, ammonia, water, begin to sublimate in response to the distant warmth. The object brightens, develops a coma of expelled gases, and eventually unfolds the magnificent tale that causes observers on Earth to pause and wonder. The perturbation caused by a passing star represents just one form of nudging. There is another, equally important mechanism at work in the Oort cloud: the tidal forces of the galaxy itself. The Milky Way is a vast disk of stars, gas, and dark matter, rotating around a distant galactic core. As our sun orbits that core, a journey that takes roughly 250 million years, it passes through regions of varying gravitational influence. The concentration of stellar mass in different directions shifts and sways. These differential gravitational forces, stretched across the enormous distances of the Oort cloud, create what astronomers call galactic tides. Unlike the tug of a single passing star, galactic tides are a constant, slow influence. Imagine holding a sphere of tiny objects suspended in a gravitational field that is slightly stronger on one side than the other. That differential force acts to stretch and compress the cloud, subtly deforming it over time. Oort cloud objects on the side of the cloud facing the galactic center experience slightly stronger gravitational tugging than those on the far side. This asymmetry, persistent and patient, gradually alters the orbits of countless objects. Some are pulled inward toward the sun, others are flung outward, even more deeply into the cold dark. The galactic tide, though weak compared to the sun's gravity at closer distances, is relentless. It works on timescales of millions of years, but it works nonetheless. How often, then, do these nudgings actually result in a comet falling inward to become visible from Earth? The probability is remarkably low for any individual object in any given year, and yet the timescale is so immense that the outcome is assured. It is estimated that gravitational perturbations from passing stars and galactic tides could knock an Oort cloud object toward the inner solar system perhaps once every 100,000 years or so, though such estimates carry considerable uncertainty. This frequency means that in any human lifetime, the chances of observing a newly arrived long-period comet are modest but real. Over billions of years, however, the steady stream of inbound objects continues, a gentle cascade of ancient wanderers returning from exile. The physics underlying these perturbations touches on something profound about the universe. Nothing is truly isolated. The Oort cloud, for all its isolation, for all its darkness and distance, remains connected to the galaxy in which it dwells. It is subject to the gravitational choreography of the Milky Way, to the slow dance of stars drifting through space, to the patient tidal forces that reshape the cosmos on timescales so vast that human history seems like the blink of an eye. Each passing star, each galactic tide, writes its influence on the cloud, and from time to time, one of these whispered nudges sends an object tumbling inward, beginning a journey that will end in brightness and spectacle, viewed by creatures on a distant blue world who gaze upward in awe. There is something almost poetic about the way astronomers trace the journeys of the great comets backward through time, as though following a thread that leads from the night sky where we once saw them, back through the darkness, back through decades or centuries of empty orbit, back finally to the ancient cloud that birthed them. Hale-Bopp, that brilliant visitor of 1997, whose pale green coma stretched across the evening sky like a ghostly brushstroke, arrived from somewhere far beyond the ordered planets. And when astronomers calculated its trajectory, when they ran the mathematics of its orbit backward into deep time, the path led them inevitably to a conclusion both humbling and awe-inspiring. This comet had slept in the Oort cloud for roughly 4,000 years before something stirred it into motion, before some gravitational whisper nudged it from its frozen slumber and set it falling, at last, toward the sun. The mathematics of long-period comets is in itself a gentle revelation. These are not the short-period visitors, the Halleys of the solar system that return with clockwork regularity every few decades or centuries. The long-period comets obey a different rhythm entirely. Hale-Bopp will not return for another 2,400 years. It will spend that immense span of time in the cold vastness of the Oort cloud, drifting among billions of its siblings, moving so slowly that the word motion itself seems almost metaphorical. Yet the path it traced, the orbital mathematics that describe it, point back to a place of origin that only makes sense if we accept the existence of this vast reservoir of icy debris. Without the Oort cloud, these comets would be orphans, their origins mysteries. Halley's Comet offers another thread to follow. This is perhaps the most famous comet in human history, returning with a rhythm of roughly 76 years, visible to the naked eye, bright enough to inspire wonder and occasionally dread in the hearts of those who witnessed it. Yet even Halley, for all its familiarity and its regular cadence, likely began its journey in the Oort cloud, at some distant point in the past. Its current orbit, which brings it reliably back to the inner solar system, represents something like a shortened version of a longer story. Astronomers theorize that sometime in the distant past, perhaps tens of thousands of years ago, Halley was flung inward from the outer cloud, and then gradually captured into the gravitational embrace of the giant planets, nudged into a more regular pattern of return. What was once a rare wanderer, subject to the slow random drifts of the Oort, became something almost domesticated, almost predictable. This speaks to one of the subtle truths about long-period comets. They are like visitors from another age, remnants of the solar system as it was billions of years ago, when it was far more chaotic, far less orderly than it appears today. Each comet that enters the inner solar system and passes near the sun carries within it a kind of ancient memory. Its composition, the ratios of various ices, the dust and rock embedded within it, all of this speaks to the conditions in the solar system at the moment of its formation. In this sense, studying comets is rather like listening to stories told by the very old, those who remember the way things were when the world was young. The visual memory of Hale-Bopp in the spring of 1997 remains vivid for many observers. A double-tailed apparition, brilliant enough to see even from light-polluted cities, it drifted slowly across the night sky, its movement so gradual that one could scarcely detect it from night to night, yet undeniable if you watched across the course of weeks. And somewhere in the calculations of its motion, in the careful astronomical observations that tracked its path, there was an implicit acknowledgement of where it had come from. The Oort cloud is not merely theoretical, not merely a mathematical convenience invented to explain observations. It is the ancestral homeland of these visitors. It is the place from which they emerge. There is something quieting about this knowledge. The great comets of history, the ones that blazed across the sky and inspired fear or wonder in the hearts of observers, that sparked the composition of poetry and music, that were recorded in chronicles and temple walls, They all came from the same cold, vast, ancient reservoir. They spent immeasurable ages drifting in the darkness, and then some force, some chance encounter with a passing star or a gravitational tide from the galaxy itself, set them on a path toward the sun. For a brief moment in their history, a moment that might last only weeks or months, they would be visible to human eyes, and then they would turn and travel outward again, back into the cold, back into the waiting dark, to drift for thousands or millions of years before another stirring might bring them home again. And as we picture these countless icy bodies drifting in their slow, gravitational choreography, a quieter possibility emerges from the realm of theoretical astronomy, one that astronomers are still carefully examining, still turning over in their minds like a smooth stone held in dim light. It concerns not the objects born alongside our solar system, those ancient planetesimals scattered outward in our sun's turbulent youth, but rather something far stranger, something that may have arrived here from somewhere else entirely. You see, the Oort cloud exists in a region where the sun's gravitational dominion begins, ever so gradually, to loosen its grip. And in that liminal space, where our sun's influence fades into the vast emptiness between stars, other stars are also passing by, not close, never close by cosmic standards, but near enough over the course of billions of years that their gravity can leave an impression, can exert a subtle pull. And that raises a profound question that keeps some astronomers awake in the most reflective hours. Could some of the objects now orbiting our sun have actually been born around other stars entirely, only to be stolen away by our sun's gravity as they drifted near? The concept is known as gravitational capture, and it is not merely speculation without foundation. It is grounded in the physics of how binary star systems work, how stellar encounters reshape the orbits of nearby bodies, and the Oort cloud, with its vast expanse and its position at the threshold between our solar system and interstellar space, is precisely the kind of region where such captures might occur. An object wandering through the sparse darkness between stars, flung loose from its original sun millions of years ago, could encounter our own star. And if the geometry is right, if the velocities align in just the correct way, our sun's gravity might gently draw it in, holding it in an elongated orbit, adding it to our cloud. This is not yet established fact. It remains an open question, a beautiful and humbling uncertainty that defines the frontier of modern astronomy. Some models suggest that a small percentage of Oort cloud objects may have origins beyond our sun. Others remain skeptical, pointing out that such captures would be vanishingly rare across the age of the solar system. The evidence is circumstantial at best, yet the possibility itself speaks to something profound about the interconnectedness of the galaxy, about how the sun's gravity may cast a wider net than we once imagined, drawing in orphaned wanderers from the dark spaces between stars. What makes this question particularly intriguing is how difficult it would be to detect such an object, even if it existed. An interstellar refugee would orbit silently among billions of other frozen bodies, each one appearing much like any other to our distant instruments. Its chemistry might hold clues, isotopic signatures perhaps, or chemical compositions that differ from what formed locally in our solar system's dust disk. But those clues are subtle, requiring the closest of close study, and most Oort cloud objects remain forever invisible to us, too distant, too small, too dark. Yet occasionally, an object from the Oort cloud is perturbed inward by a passing star or the slow tidal influence of the galaxy itself, and it begins its long fall toward the inner solar system. It becomes a comet, a blazing messenger, carrying with it whispers of its origin. And astronomers watch these visitors with particular attention, hoping that someday one might arrive bearing the unmistakable signature of a different sun, a different genesis, proof that our Oort cloud contains not only the offspring of our own solar system's birth, but also refugees from the stellar nurseries of other distant stars. The truth is that we simply do not know how many, if any, such objects exist within our cloud. This is the honest acknowledgement of science at its frontier, the willingness to ask difficult questions, to sit with uncertainty, to recognize that the universe may be organized in ways we have not yet discovered. Perhaps future observations, more sensitive telescopes, or perhaps one day a spacecraft with instruments refined enough to analyze the composition of a distant comet might reveal whether our Oort cloud truly is a repository of stellar wanderers, or whether it remains purely a solar system reservoir, born only from the sun's own chaotic infancy. And in that uncertainty lies a kind of peace, a reminder that even after centuries of observation, even as our understanding of the cosmos deepens and grows more nuanced, there remain mysteries that rest gently in the spaces between what we know and what we can only wonder about. The Oort cloud keeps its secrets still, turning slowly in the dark, holding within it questions that may take generations more to answer. There is a peculiar moment, very hard to pinpoint on any map, where something invisible shifts. It is not a wall, it is not a line drawn across the void. And yet somewhere out there, in that fathomless darkness beyond the outer reaches of the Oort cloud, the sun's gravitational embrace begins to loosen, to fade, to release its ancient claim on the objects that orbit it. This is the true edge of the solar system, or rather, this is where the question of what the solar system actually is becomes wonderfully, troublingly uncertain. For centuries, we imagined the edge of the sun's domain to be something fixed and final. We drew our planetary borders, sketched our asteroid belts, and felt a kind of closure. The solar system ended where we said it ended. But as our understanding deepened, that comfortable boundary dissolved. If the solar system is defined by gravitational influence, then the sun never truly loses all its pull. It stretches outward infinitely, weakening with distance, but never entirely ceasing. A photon from the sun travels freely through the void. A massless particle would feel the sun's gravity forever, diminishing but persistent, pulling always at the edges of existence itself. And yet there is a threshold of sorts, and it is one of the most humbling realities in astronomy. Beyond a certain distance, somewhere nestled in the vast envelope of the Oort cloud's farthest reaches, perhaps 200,000 astronomical units from the sun, or even further, the gravity of other stars begins to matter more than the sun's. A wandering star from a neighboring system, drifting through the local neighborhood of the galaxy, exerts a pull that rivals or exceeds the sun's ancient, weakened tug. At that point, the distinction blurs entirely. Is an object still part of our solar system if another star's gravity has become equally significant? Does it belong to us, or to them, or to the galaxy itself? This is where physics becomes philosophy, and precision becomes poetry. Imagine, if you would, a small icy body drifting out there at the cloudmost reaches, a silent witness to an immense and gentle cosmic boundary. Behind it, the distant sun, a point of light no brighter than Venus appears to us, already dimming in the memory of deep space. Ahead of it lies true interstellar emptiness, where no single star claims dominion. It exists in a borderland, equally pulled by two gravitational masters, belonging fully to neither. And this boundary is not static. As stars move through the galaxy, as the Oort cloud itself migrates with the sun's slow orbit around the galactic core, this threshold shifts. The edge of the solar system is not a fixed thing. It is a breathing membrane, forever negotiating with the universe around it. What makes this so profoundly calming to consider is the realization that all such boundaries are, in a sense, illusions. We impose them for the sake of understanding. We say the solar system ends here, the galaxy begins there. But nature recognizes no such demarcations. Gravity is a conversation between all things, immediate and distant. It is a continuous spectrum, not a hard switch. The sun's gravity never truly stops. It only grows so faint that other forces become comparatively loud. This redefinition of the edge, from something sharply drawn to something profoundly gradual, teaches us something essential about the universe's true architecture. There are no walls between things. There are only gradients of influence, zones of transition, places where one system's dominance quietly yields to another's. The solar system does not end abruptly. It fades, it merges. It dissolves into the larger structure that surrounds it, and that larger structure, the galaxy itself, is likewise embedded within gravitational fields that extend across incomprehensible distances. When we trace this logic outward, we arrive at a gentle, almost melancholic truth. Nothing is truly isolated. Everything is part of a larger web. The sun orbits the galactic center. The galaxy orbits through a local cluster of galaxies. Even galactic clusters are gravitationally bound to larger structures, cosmic filaments, and vast voids that comprise the true skeleton of creation. At every scale, from the smallest icy moon in the Oort cloud to the grandest filament of galaxies, the pattern repeats. There is always something larger, always something beyond, always a boundary that proves softer and more blurred than we imagined. This is perhaps why contemplating the Oort cloud's true edge brings such quietude, because it reminds us that the question of where we are, where our home, our solar system truly ends, has no crisp answer. We exist within a nest of gravitational hierarchies, each one folding into the next, stretching infinitely outward. The sun keeps us, the galaxy keeps the sun, and the universe keeps it all. And somewhere out there, at a distance we can only approximate, in a region we will never see directly, the sun's ancient light continues to fade. The darkness deepens, and still, invisibly, the pull continues, a whisper that will never entirely vanish. Humanity has sent forth its most ambitious messengers into this realm of ancient ice and bottomless silence. Voyager 1, launched in 1977, has become something of a celebrity among our deep space probes, a fragile machine carrying golden records and the dreams of an entire generation outward into the void. For nearly 50 years now, it has been traveling, crossing vast stretches of our solar system, leaving behind the orbits of the planets one by one until even distant Neptune fell away behind it. And yet, despite this extraordinary journey, despite the decades of faithful transmission and the unfathomable distances it has already traversed, Voyager 1 remains nowhere near the true beginning of the Oort cloud's innermost reaches. To truly grasp the humility this imposes upon us, consider the numbers with a kind of quiet awe. Voyager 1 has traveled roughly 24 billion kilometers from the Sun as of recent years. That sounds, on the surface, like a number almost too large to fathom, but the Oort cloud begins around 2,000 astronomical units from our star. And remember that a single astronomical unit is the distance from the Earth to the Sun, roughly 150 million kilometers. 2,000 of those distances. That means the inner edge of the Oort cloud lies somewhere around 300 billion kilometers away. Voyager 1, for all its noble wandering, has not yet reached even 1/10 of that distance. Your mind might pause here, wondering at what this means. It means that if Voyager 1 were somehow plucked from its current trajectory and redirected straight toward the Oort cloud with no further acceleration, it would take approximately 70,000 years, perhaps longer, to arrive at that inner threshold. 70,000 years. Humanity has existed for a mere fraction of that span. We have built civilizations, watched empires rise and crumble, journeyed from caves to the threshold of the stars, and in all of that, we have not even managed to age enough as a species to see one of our own creations approach the Oort cloud. Voyager 2 travels alongside its twin in a different trajectory, also launched in 1977, also pushing outward into the darkness with the same patient resolve. Both vessels were designed to visit the giant planets, a task they accomplished with remarkable success. They conducted flybys of Jupiter and Saturn, studies of Uranus and Neptune that revealed wonders we had never before witnessed. Those encounters were the apex of their mission in many ways, the moment when they performed their intended science. And then, having completed their work in the realm of the planets, they simply kept going, coasting on their momentum and the sun's fading gravity, outward, ever outward, into the region beyond all the orbits. This is perhaps the most poignant truth about our furthest travelers. They were never designed for this journey. They were not built with the intention of exploring the Oort cloud. Their instruments are slowly failing, their power sources dwindling as the radioisotopic thermoelectric generators that power them decay with the inexorable march of radioactive half-lives. It is pure chance and the laws of physics that allow them to continue onward at all. They send their whispers back to Earth, signals that take hours to arrive, confirming their existence and their location. And with each passing year, the time it takes for those signals to reach us grows longer, until soon they will become so faint that we may lose contact entirely. The spacecraft carry messages from Earth, those golden records meant for whatever intelligence might find them in the unfathomable future. Among the sounds recorded are whale songs and the laughter of children, greetings in countless human languages, classical music, and the heartbeat of our planet. These records are now in a place where no signal from Earth can reach them, no rescue is possible, and no human being could survive. They are, in a very real sense, messages in bottles cast into an ocean that has no shores. They might drift through the Oort cloud for billions of years, untouched and unheard, the last proof that we ever existed. And yet there is something deeply beautiful in this futility, is there not? Even knowing that our fastest, most sophisticated machines will never reach the Oort cloud in any human time frame, we sent them anyway. We sent them out of curiosity, out of a need to understand, out of a desire to push against the boundaries of the known and glimpse what lies beyond. Voyager 1 and 2 represent something essential about our species, the willingness to build things we know we will not live to see completed, to send forth our knowledge and our hope into regions we may never explore ourselves. When we consider the Oort cloud from this perspective, from the vantage point of spacecraft that have devoted decades to traveling and remain impossibly far from their destination, the cloud transforms into something more than just a repository of ancient comets. It becomes a monument to time itself, a region so vast and so distant that it refuses to yield to our current tools and methods. It stands as a quiet reminder that despite our achievements, despite the sophistication of our technology and the breadth of our understanding, there are still frontiers that remain utterly beyond our immediate grasp. The Oort cloud waits. It has been waiting for billions of years, and it will continue waiting long after Voyager 1 and 2 have fallen silent, drifting still in that profound and patient darkness. And yet, in all this vastness, all this apparent randomness of icy bodies drifting in their appointed orbits, astronomers have begun to notice something peculiar. When they map the trajectories of Oort cloud objects, when they trace backward through space and time to imagine where these ancient wanderers once gathered before being scattered outward, a certain clustering emerges, not random, not what we might expect if Jupiter and Saturn alone had flung all these bodies into the deep. There seems to be a subtle bias, a gentle preference towards certain orbital angles, certain groupings that whisper of influence from something more distant still. This is where our story turns toward mystery, toward the realm where careful observation meets thoughtful speculation. Astronomers began to ask, what if the young solar system harbored other inhabitants beyond the 8 planets we know today? What if a massive body, far heavier than Earth, had once wandered through the outer reaches, pulling and pushing the Oort cloud into its current configuration before being ejected entirely into interstellar space. Such rogue planets are not merely theoretical. We know from studying other star systems that planetary migration and ejection are commonplace. Why should our solar system have been different? The evidence, subtle though it is, suggested that something significant may have sculpted the Oort cloud's arrangement. The clustering of these distant bodies, their tendency to occupy certain orbital spaces more frequently than others, hinted at an architect. And so emerged the hypothesis, increasingly discussed among cosmologists and planetary scientists, of a potential ninth planet. Not Pluto, which we've long since reclassified, something else, something larger, something far, far beyond Neptune's current orbit, moving in a much slower, much grander dance around the Sun. This hypothetical world, sometimes called Planet 9 in recent literature, would exist at distances so extraordinary that its single orbit around the Sun, would span tens of thousands of Earth years. A planet that circles once while humanity rises and falls through 10,000 generations. Its gravity, though distant, would be profound. If such a body exists, it would act as a cosmic sculptor, its pull subtle but persistent over millions of years, reshaping the distribution of Oort cloud objects in ways we're only beginning to understand. The clustering patterns we observe might be the fingerprints of its ancient passage. Yet we must tread carefully here. This remains speculation, informed and grounded in genuine observational puzzles, but speculation nonetheless. We have no direct evidence of Planet 9. No telescope has captured its image. Its existence remains an open question, a problem that keeps astronomers awake not with worry, but with the deep satisfaction of genuine mystery. For what is science but the gradual illumination of questions that resist easy answers? And what better question to sit with in the darkness than this? Might the solar system harbor secrets we have yet to discover? Some researchers suggest that other explanations might account for the Oort cloud's structure. Perhaps the passage of a nearby star, early in the solar system's history, left its imprint. Perhaps the collective gravity of the Oort cloud's own thousands of billions of objects creates the subtle biases we observe. These too are reasonable hypotheses, each with merit, each awaiting further evidence. The truth is that the Oort cloud, distant as it is, remains difficult to study directly. We infer its existence through the comets it occasionally sends toward us. We map its likely properties through mathematical models and computer simulations. We read its nature in the mathematics of orbital mechanics, in the careful measurements of astronomers working to understand the solar system's deep past. And perhaps this is the deeper comfort of such mysteries, not that we lack answers, but that the universe still holds questions worthy of our attention, that even with all our telescopes, and all our theoretical understanding, the solar system retains corners of profound mystery. The Oort cloud, in this sense, represents not a failure of our knowledge, but an invitation to deeper understanding. Whatever shaped its present form, whether Jupiter and Saturn alone, or whether some ancient wandering giant left its mark, the result is the same: a vast silent repository of ancient material, holding within itself the seeds of tomorrow's comets, the testament to a young solar system's violent creative youth. The notion of Planet 9, whether it exists or eventually proves to be an artifact of incomplete data, illustrates something important about how science evolves. We observe anomalies, we devise explanations, we test them against existing observations. If they hold, we search for new ways to confirm or refute them. If they fail, we return to the drawing board with deeper insight. This is not frustration. This is the very engine of discovery, turning slowly, patiently, toward truth. And so we arrive at something like stillness. The Oort cloud, in all its vast and patient immensity, exists as perhaps the most profound archive the solar system has ever created. Here, suspended in the deep cold beyond the reach of almost everything, drifts a memory of the beginning itself. These billions upon billions of icy objects, some no larger than a modest mountain, others the size of small cities, have waited here in near-perfect silence for 4.5 billion years. They are the preserved remainder of an era when the solar system was young and chaotic, when gravity was rewriting the orbits of worlds, when material was still finding its place in the cosmos. Each fragment carries within it something like a fossil record, frozen in both time and temperature, holding chemical signatures from the earliest moments of formation. What a strange comfort there is in imagining these ancient stones and ice, orbiting slowly through the darkness, asking nothing of the universe, and receiving nothing but occasional whispers from passing stars. They do not warm, they do not decay, they simply endure, and in their endurance they preserve. The Oort cloud is, in essence, a library written in ice and stone. Every object that drifts there tells a story about the conditions that existed when the solar system was born, about the forces that shaped it, about the violence and beauty of that distant age. To contemplate it is to hold in your mind the whole history of our cosmic neighborhood, compressed into a sphere of profound quietness. Consider how, even now, as you rest in the stillness of this moment, light from the distant sun, that light which warmed your face today, which has guided life on Earth for billions of years, is arriving at the Oort cloud as barely more than a whisper. It takes hours for that light to reach there, and when it arrives, it is so faint as to be almost meaningless. And yet even at such distances, even in such darkness, the sun's gravity persists. It holds, it reaches out across the incomprehensible void and keeps these objects in their orbits, bound by a force that operates in silence and requires no acknowledgement. This is the deepest expression of gravity's patient authority. Not the dramatic dance of planets or the violent collapse of stars, but the quiet, eternal holding of ancient ice in the darkness. There is something deeply settling about the Oort cloud's existence, precisely because it is so remote, so removed from any possible touch or interference. It will never be colonized, it will never be mined, it will never become a place of human concern or conflict. It will continue its slow, eternal rotation around the sun, this frozen cathedral of deep time, long after the Earth itself has vanished. The eons unfold there at their own pace, unmeasured and unmeasurable. 1,000,000 years passes as a single moment for the objects in the Oort cloud. 10 million years as an exhale. They know only the cold, the faint pull of gravity, the rare encounter with a passing star that barely deflects them from their courses. They know only the vastness. And perhaps there is a teaching in that. Perhaps there is something to be learned by contemplating a place where nothing hurries, where nothing struggles, where everything simply exists in the most patient form of rest imaginable. The Oort cloud asks us to consider what it might mean to be held in place by forces so ancient and so fundamental that they require no effort to understand, only to acknowledge. Here, at the edge of the sun's domain, in the place where the solar system fades toward the interstellar night, we find a kind of peace, a kind of stability that comes not from action or vigilance, but from being held in a pattern that will not change for billions of years yet to come. The objects that drift in the Oort cloud are, in a sense, safe. They are protected by their distance, preserved by their cold, kept whole by the gravity that binds them to a sun they barely know exists. They will remain in this sanctuary long after this moment has passed, long after you have drifted into sleep and forgotten these words. They will remain through the rise and fall of civilizations, through the ages of human history yet to come, through the slow burning of the sun across its remaining billions of years. And in that eternal waiting, in that absolute stillness, there is something like contentment, something like the deepest form of rest. As you drift now, imagine the Oort cloud surrounding the solar system like an invisible ocean, a sphere of ice and stone that encompasses everything we know and everything we are. Imagine the objects within it, turning slowly in their ancient orbits, asking nothing, needing nothing, simply being. They are older than pyramids, older than mountains, older than the first moments consciousness ever flickered in the universe. And they will be here long after everything we build has turned to dust. There is a profound peace in that knowledge. There is a settling of the mind that comes from truly understanding how small our concerns are, how brief our moment, and how vast and patient the cosmos truly is. The Oort cloud drifts on, eternal and unchanging, a silent, frozen archive of memory and time, and in its endless peace, perhaps we too can finally rest.